So good afternoon, welcome to the ASIC seminar series. Today is our pleasure to have Professor Steve Reising with us. Dr. Reising is a professor in the Electrical and Computer Engineering Department at Colorado State University in Fort Collins. He received the PhD degree in electrical engineering from Stanford University, where he was supported by a NASA fellowship. And his research interests focus on remote sensing of Earth's atmosphere and oceans from airborne platforms and small satellites, as well as passive remote sensing radiometer systems based on the low noise microwave integrated circuits from microwave to sub-millimeter wave and terahertz frequencies. He has been the principal investigator of 14 grants from NASA, NSF, DOD, ONR, Naval Research Laboratory, and so on. And Dr. Reising has served as associate editor of IEEE Geoscience and Remote Sensing Letters. He has served as advisor for 14 master and PhD students who are currently employed by university, industry, government laboratories across the world. So let's welcome the speaker.
Thank you very much, John. Thank you for having me. Thank you for such a great turnout, and also to the people on the webinar. The webinar people may ask questions through the chat room. They wanted me to say that. So it's great to be back in College Park. I lived at the University of Maryland for a summer when I was a grad student visitor 25 years ago at Goddard. And remember I bought a bicycle to ride back and forth between College Park and Greenbelt. And it would cost $25. So I learned bicycle repair skills during that summer. And I found some good parks to ride through and so on. So I'm going to like to talk about new observing capabilities of passive microwave radiometers on CubeSat, specifically Tempest T, Temporal Experiment for Storms and Tropical Systems Technology Demonstration Mission. It's a mouthful. This is led by Colorado State University. We lead the science and validation part with Professors Kumaro and Chandra and Dr. Westberg, and then along with our postdocs and students, of course. Then the instrument was built by JPL, and the project manager was Todd Geyer before launch, and Shannon Brown after launch. Here this pointer works. Sharmila Padmanabhan was instrument manager. She got her PhD about 10 years ago from my group at Colorado State. And then Boon Lim from University of Michigan, who was one of Chris Ruff's students and had an important role in the project, and as well as then Blue Canyon Technologies, small company in Boulder, Colorado. They provided the spacecraft, did the integration of the instrument into the spacecraft, and they do mission operations. And NASA Wallops takes care of the ground station. We do UHF communications. So we first start with 3 images of a Category 5 hurricane that was the furthest east in the Atlantic for Category 5s. It had some interesting history. But the point is we have 3 microwave images from satellites. And you probably wouldn't guess just by looking at these images that 2 of them were taken by world-class kind of large instruments, AMSR-2, SSMIS, that have been around for a while, and one of them has been operating for 13 months, and that's Tempest T, the middle one. So then we look at the whole global view, and we have a sensor A on the top, sensor B on the bottom. So the question is, can you guess which one is which? Well, maybe by the swath size and the orbital characteristics, but not necessarily by the quality of the data. Sensor B is ATMS, NOAA ATMS, 75 kilograms of mass, 100 watts of power, and my students say $4 signs on Yelp. So Tempest T is about a factor of 20 smaller in terms of mass and power consumption. And here's a team at JPL produced the instrument. That's the instrument on the table. This is Todd Geyer, Alan Tanner, Sharmila Panraban, Boone Lim, Heather Lim, and Rudy. And so Rudy Bendig, that's it. And so this takes about 4U of a 6U CubeSat. I'll explain what 6U CubeSat is here, but you see it with the solar panels unfurled. That's in the lab when it was integrated at Blue Canyon Technologies in Boulder, which is about an hour south of us from Fort Collins. So just a few words about the CubeSat Standard. For those who aren't familiar with it, it was formalized 20 years ago by Bob Twiggs at Stanford and Jordi Puig-Suari at Cal Poly in San Luis Obispo as a 10-centimeter cube. So that's the unit. 1U is a 10-centimeter cube with 1.3 kilograms of mass. And so we use not only a 1U satellite, but build them up by adding U's together. And so it's not quite exactly 10 centimeters. The third dimension is longer, but the point is we can add those up into, typically 3U might be a typical size right here of 34 by 10 by 10 centimeters and up to 4 kilograms. But then the last couple of years, we moved up to the capabilities, to increase capabilities, we moved up to 6U. So it'd be like placing these two next to each other and getting a dimension of 34 by 20 by 10 centimeters. And then because of the deployers and the characteristics of the standard, we allow up to 50% increase in mass density. So it's not 8 kilograms, but 12 kilograms. And so basically this gives us increased solar panel area for battery charging and potential for more redundancy in satellite to ground communications, potentially improved calibration, and just larger area for the satellite. There are also different groups are looking at 12U. It's not exactly a strong standard for deployers yet, but that may change very quickly. So just to give an idea of worldwide, 1,000 CubeSats have flown in the last 20 years. This is Professor Michael Swartout at St. Louis University. He's been keeping track of this for some time. He keeps track of success rate of CubeSat missions and so on. But then if we look, we look at the growth, it's gone beyond, it went beyond about 50 satellites per year only in 2012. So that's quite recent. And if you look at the mission types, you can see that a lot of them in...
Oh, no, you're fine.
Oh, I'm fine. Okay, great. So a lot of them in 2017 were for Earth imaging. You may have known about the Planet company in San Francisco that deployed 100 all at once, and they were launched from India in the PSLV rocket. So this is a worldwide phenomenon. It allows countries that have never been into space before to get into space. And then, but the real point is that a lot of people thought of it more like education. In the early years, people thought of it, this is just something to do, something to throw something into space and see if it works. But then, through infusion of money from NASA and other organizations, it's become a science capability. And so you see that the percentage of missions actually doing science or for science are pretty small. The percentage is pretty small in yellow, but there are a lot of tech demos here in the bright red. So that then can show the capability to do science. So we started off Tempest a number of years ago when we proposed to launch 5 identical 6U CubeSats, each with an identical 5-channel millimeter wave radiometer or upper microwave radiometer flying 5 minutes apart. And so the idea is to take advantage of the capability of CubeSats to be able to deploy more of them than just one, and specifically to be able to space them out in a train of satellites. So some people called it string of pearls and so on. But this is a train of 6U CubeSats with millimeter wave radiometers. This was the proposal to sample rapid changes in convective activity and the surrounding water vapor environment every 3 to 4 minutes. So these are basically microwave sounders if we deployed them every 3 to 4 minutes for up to 30 minutes, that would take, up to 8 satellites. And then it could address one of the most important science questions from the 2017 National Academies of Science Decadal Survey: why do convective storms, heavy precipitation, and clouds occur exactly when and where they do? So that's a big question, but it could contribute to that. So what we got was a tech demo mission, and that started, the grant started on August of 2015, and then 2.5 years later, in early 2018, we delivered the 6U CubeSat with the radiometer instrument ready for launch. And the launch was provided by the CSLI, which is the CubeSat Launch Initiative, that provides free launches for NASA centers, nonprofit organizations, and educational institutions. But, that's probably not, the launch is probably not the biggest cost, depending on the orbit you need. So we launched on a resupply mission to the International Space Station with ATK, which is now north of Greenwich, on the commercial resupply service 9 on May 21st of last year. And then we deployed in orbit about 2 months later. And that was from the Japanese experiment module with the robot arm. And so I think it was 7 CubeSats deployed that day, all 6U CubeSats. And so this is showing the concept of 8 identical CubeSats, Tempest CubeSats, and then observing a number of storms. An analysis of how many satellites would observe the storm and with what delay. And so this is an opportunity to uniquely sample convective activity, or the development of convection, individual convective cells over a 3 to 30 minute time scale. And it's complementary with existing missions, which are, of course, science missions and much larger, especially the GPM. As you know, many people are heavily involved with GPM, and some that are here. And so, the point is that Tropics is a mission which is planning to deploy in 2021 6 CubeSats in 3 different orbital planes to be able to get relatively frequent observations of tropical cyclones, hurricanes, typhoons, and they go down to a time scale of just under an hour. So we would right here. So we would be on the 3 to 30 minute time scale here, and provide a unique observational space and more frequent observations than are enabled on a regular basis by Tropics or GPM. So here is the 6U spacecraft. Some people are interested in learning a little more about the spacecraft. So this is now a pretty standard product. These is XB line. This was the first one, XB1, from Blue Canyon Technologies. So about, I think it's 1.5 U is used out of the 6U, used for the avionics module. The avionics module provides 3-axis torque rods, 3-axis reaction wheels for very precise attitude control, and GPS antenna and 2 star trackers as well for attitude determination and obviously location determination, as well as the flight computer, and the communications too. So here is Global Star antenna. That's our backup communication S-band. Our main communication is UHF. Blue Canyon designed a UHF antenna, which is used with the Cadet U radio in this spacecraft. They're using newer radios right now, moving into S-band and so on. So 4U out of the 6U is encompassed by the instrument, and then there are 2 solar arrays. Actually, one of these 6 panels is not populated because it holds down the radiometer antenna that I'll show you, before deployment of the solar panels. So in any case, there are 5 solar panels, and when we get into the instrument, that's more, that's our specialty, and I'll show you that we've been developing this technology for over about a decade in various programs, mostly sponsored by NASA's Earth Science Technology Office, or ESTO. And the Tempest T instrument does cross-track scanning, just like operational microwave sounders. The calibration setup allows us to observe cosmic microwave background and the calibration target made by Zach's millimeter wave right here every 2 seconds. So it rotates at 30 RPM. It gets measurements of the Earth scene, the ambient calibration target, and the so-called cold sky or cosmic microwave background every 2 seconds. And the spatial resolution varies from 13 kilometers at our highest frequency of 181 gigahertz near the water vapor line at 183, and to 25 kilometers at 87 gigahertz, so near a 90 gigahertz channel. So the technology is really innovative and new. You know, even though the chips were published about 10 years ago, they've not been used for any other Earth science mission that has done operations near this band. And so they were developed jointly by JPL. So basically this is the low noise amplifiers that allow a very low noise figure and very low uncertainty or any delta T from radiometers. And these were shown to be the highest, the record lowest noise temperature in the world of LNAs from 140 to 190 gigahertz. And this was at the International Microwave Symposium in 2008 and 2012. So since then, we've developed various stages of technology, and a lot of these have been collaborative with CSU and JPL, including other partners, Northrop Grumman for the chips. And so we've progressed, and then others are led by JPL. Of course, GeoStar is a large program trying to put a microwave radiometer synthetic aperture into geostationary orbit in the future. And then JPL's race was a 3U CubeSat that's involved in a launch failure that didn't make it off the launch pad, but nothing caused by the radiometer, obviously. So, so the ACT is an Advanced Component Technology program going from low TRL levels of about 2 to about 4. And then we moved up to a TRL of 5 on aircraft demonstration. And this was demonstrating some of the channels which are now being built for, or have already been delivered for the high frequency microwave radiometer on Sentinel-6. And JPL's built that for Europe, and they believe that'll launch in another couple years. So a year or two. So Chevy right here, Chevy Bosch Luis, he got his PhD at Polytechnic University of with Professor Adriano Camps, and he spent 5 years with me, and now he's at JPL, along with a number of my former graduates. And this is Tori Hadel. She's now at Ball Aerospace. Anyway, they flew it on the Twin Otter from Grand Junction, Colorado, for about 70 flight hours, and verified this radiometer. That's the large version of the radiometer. And then we developed a 6U CubeSat radiometer for very high frequencies to look at cloud ice particle sizing. I'm not going to talk about that today, but it's called tropospheric water and cloud ice instrument. And we're having our final IIP review next week, and we'll look at future opportunities to contribute to, particularly to ACCP. So the culminated, all these technology developments culminated in NASA Earth Venture Technology demonstration of Tempest T. So here is the instrument of Tempest T. Just a few things. This is, okay, so the axis of rotation is vertical, and the offset paraboloid reflector directs the radiation from the atmosphere onto, or the surface, onto the feed horn that was developed in the ACT project, and that just splits it between the W band around 90 gigahertz and G band. G band has 4 frequencies from 161 to 184 gigahertz, and the change here in technology is partly that it's direct detection. So direct detection saves power, it saves mass by not having an LO, and it has substantially, for instance, twice the twice receivers that I pointed to there compared to IceCube, launched by Goddard, a very successful 3U CubeSat. Compared to IceCube, this is about an order of magnitude less power per channel when we look at a single band that we're measuring. That's what I mean. So this is covering 4 frequencies, for instance, for cloud ice particle sizing. So building on new generation, building on the success of IceCube. So so we have at G-band the radiometer front end based on the low noise amplifiers that I showed you. We have an active power divider, waveguide based filter bank, and detectors that are tuned for these frequencies. Okay, so that's all the geek gear I'll get on this. And then we have one channel at 87 gigahertz. And then of course the signals are conditioned and packetized and sent to the ground using command and data handling system here. So, and the ambient calibration target that I mentioned is right there. So we, of course, did plenty of pre-launch calibration. We did thermal vacuum tests for environmental tests, both with the instrument at JPL, and then after it was integrated into the spacecraft at BCT in Boulder, Colorado. And so here is a measurement in TVAC at BCT. This is probably January 2018. Just a few months before we delivered, and we measured across all instrument temperatures that we might encounter on orbit. The orbit control or the temperature control is quite narrow in terms of the variation over each orbit, and so important thing to point out here is that the pre-launch and the on-orbit NEDT, so basically the smallest signal we can measure, are agreed very well, and they range from 0.7 Kelvin from 87 to 181 gigahertz. And this is for 5 milliseconds integration time. So that's shorter than some other instruments that we'll compare to it in a little bit. So just a picture from the launch. This was in the middle of the night, about 2 a.m. It launched. Or we had to meet them about like 1:30 a.m. So don't quote me on the time, but we had a significant subset of the team here from CSU, JPL, and also NASA headquarters. So we had a very good launch there from orbital ATK, and then, as I mentioned, 2 months later, into orbit. So this is a video you may have seen. Michael Freilich, Dr. Michael Freilich shows this. Showed this a number of times before he retired from NASA Earth Science. And so it had a dramatic kind of open its wings that was unexpected anomaly, but it worked out fine. So so they snapped into place right as they were supposed to, and then Cubert did what it was told. It deployed its wings later, or its solar panels later, and actually. The cross sections are pretty similar, so that allows us to do some orbital drag experiments between these two because they were at different attitudes at different times. But anyway, Cubert is a 6U CubeSat as part of the NASA's INVEST program under Earth Science Technology Office, and that had it demonstrated first wideband RFI mitigation system on a satellite. Much wider than SMAP, for instance, in L-band. Okay, so we got our first light after some communication, work. We got our first light on September 11th, 2018, and we didn't get 100% of the data, but if you look here in the Atlantic sector toward the tropics, we got 3 hurricanes all on that first day, just from those first orbits that I showed you. We captured Hurricane Florence. So this is the visible, the GOES images to show you what they are. And this is 164 gigahertz brightness temperature. Florence, Isaac, and Helene. And so that's on the first day. And then so that was what? September 2018. And so this is beginning of September 2019. We observed Hurricane Dorian. This is an animation of the kind of hurricane track you can do from these low Earth orbit passive microwave sounders. So of course that's been done before from the big operational sounders, but this is, not knock on wood, this is our second hurricane season that we're viewing, and then of course we can get some altitude resolution from water vapor profiling of channels near 183 gigahertz. So this is 10 days running. We tracked Hurricane Dorian, and we had a nice press release about that too from JPL and NASA. So we've also looked at heterogeneous sensors and the idea of heterogeneous sensors in small satellite constellations. JPL launched the RAIN radar, which is a Ka band RAIN radar called RAINCube. You may have heard Simone Tonelli talk about it, or Eva Peral or others. So we got some simultaneous measurements with them. As you can see, they're a very different drag profile. They deployed a half-meter antenna, so they're not going to stay with us in the orbit. But the initial orbit was similar. And so we got a simultaneous flyover of Typhoon Trami just 3 weeks after our first flight. And this was exciting. And then here we have the Cygnus wind field contours shown here on the horizontal plane. So the horizontal plane measurement is from Tempest T. The vertical plane measurement here is from RAINCube. So that's the RAINCube RAIN radar echoes, and then we correlated them. They correlated well with where we were, where the key parts of the storm are. So that was Typhoon Trami, and then we had a coincident measurement of orographic precipitation off the Mexican coast over the ocean here, and we show some of the radar profiles and the Tempest T horizontal data there. So that was October 15th of last year, not 3 days ago. Okay, and so we had focused on individual storms, on hurricanes, typhoons, tropical cyclones, but then we get global data. Obviously we get global data, and that's something where we get a lot out of, and this is from August 15th of this year, and showing all 5 channels. So that was the 87 gigahertz brightness temperature, obviously most sensitive to changes on the surface. The atmosphere is most transparent, I guess you could say, among these frequencies at 90 gigahertz, just for an introduction. And then the 4 water vapor profiling frequencies, 164, 174, 178, and 181 gigahertz. We list only one sideband frequency because we're not doing the split kind of heterodyne that is often done when they have an IF section and double bands on either side of the gigahertz water vapor line. So anyway, that's just context. And so here are the data from August 15th. And then to show a recent day, this is October 9th. So just 9 days ago, and we're getting a good amount of data volume now, and it's always it's always great to show when we can get an entire week like this in terms of May 12th through 19th. So when I say that, that means downlinking. So our instrument operates 100% of the time, but downlinking, because we're sharing the UHF station with a number of users and some other limitations in downlink, that's really been our biggest limitation is the amount of data volume we can downlink. But we're getting pretty close to approaching real time when the conditions are very good. And so here we got a whole week of data, and that's especially useful if we want to do data assimilation experiments like we've worked on with NOAA. So if we look at the radiometer over time, over the 13 months of operations, we see that the NEDT, or the noise of the radiometer, is very stable. And so we have extremely low noise technology that I mentioned. That's the indium phosphide hemp to low noise amplifier. It's been stable over the mission to date. This is an example of some of the amplifiers and the way we integrated into the housing. And then when you consider that ATMS is integrating for 18 milliseconds, then you have to scale the NEDT from Tempest T. You scale it down by by the factor of square root of 18 over 5 to get these NEDT numbers. And so these NEDT numbers are actually lower than the ATMS NPP numbers in terms of the amount of radiometer instrument noise. So in that respect, we have improved receiver performance because we were able to inject such new technology and make it work in a system. So then the question is, when you talk about radiometer noise, you talk about stability, and then the question comes, okay, you can measure these individual cyclones, you can measure all over the globe, but how well are you doing? How well are you calibrated? So thankfully, the GPM project over 12 to 15 years has developed and really perfected, if you could say that. They've refined, it was better, the double difference technique. So the double difference technique is for cross-calibration between two sensors. And the idea is that those sensors are heterogeneous. I mean, not a microwave radiometer and a radar, but the different radiometers are heterogeneous in their center frequencies, in their bandwidth, in the viewing angles that they view the atmosphere at that time, and other characteristics. Polarization would be the main other one. So what's done is a radiative transfer integral is solved for the atmosphere for each of the two satellites. And then, so let's say for satellite 1, then the measurement is subtracted from the model, and then same thing for satellite 2. And then those two are differenced. So in the double difference, not single difference, but double difference, they remove the errors of as much as they can, of the radiative transfer model. And so what we showed is that Tempest T is within 1.3 Kelvin of the reference sensors. And if we look at the details a little bit here in this red box, we see that the 1.3 Kelvin for the mean difference, that's the absolute calibration, is only showing up in 164 gigahertz. All the others are 3/4 of a Kelvin and below. And then the stability is 0.7 Kelvin in the highest channel, and then 0.5 or below in all other 4 channels. So there are some issues which we can discuss of model uncertainty. We also will have a paper on all of this calibration and validation very soon. So the model uncertainty is larger in 164 gigahertz channel for a number of subtle and not so subtle issues, including surface emissivity, knowledge of surface emissivity around that frequency. And also there's the greatest difference between MHS frequency and Tempest T frequency at that band. The others are closer. So in any case, since we're talking about sub-Kelvin numbers, what this really means is that we have a very well calibrated and stable radiometer with very low noise. This is not my writing. This is the conservative head of GPM cross-calibration group of cross-calibrating radiometers. And they developed this process to admit heterogeneous radiometers made from many different sources into the constellation, the GPM constellation. And so this is based on 21 days of data over several seasons. We're accumulating more. Now, okay, so when we look at then the power spectral density of the data between Tempest T and ATMS, and this is in a very stable cold ocean type of situation. I believe it's in the South Pacific. Then we see that on all of the spectral scales that we're measuring, we get statistical equivalence. And so some interesting things that we can do with Tempest T being on its own satellite. So it's kind of an opportunity for experimentation that is not always available in larger satellites with a number of sensors and maybe some gyro constraints. So at least the the number of times you can do it, this kind of thing is less common for larger satellites. But with this CubeSat, we were able to just do a full 360 pitch maneuver. Just pitch right over and observe, so we could observe cold sky all through the Earth scene. And then we could, was to characterize scan-dependent biases and find that the bias as a function of scan angle before correction was a half Kelvin, and after correction was about an order of magnitude lower than that. So, so then we went ahead and did some retrievals. This is led by Professor Kumaro and a PhD student at Colorado State, Rick Schulte, who won the poster award at the AMS Joint Satellite Conference a couple weeks ago for some of this work. But in any case, the Tempest T is plotted over the NOAA MEARS retrieval from MHS satellite, sensor, sorry. And so MHS sensor we used in the cross calibration from NOAA and 2 EUMETSAT satellites. So in any case, when plotting the Tempest T over the standard retrieval, here we look at total precipitable water, or simply water vapor, cloud liquid, and cloud ice. So we find good agreement on the main features of the water vapor field, and we show no sharp gradients between the Tempest T swath and what's seen by MHS with the wider swath. And then for liquid clouds, they agree well, and also ice clouds where there are ice clouds. So some of this has been submitted as under review, led by Rick Schulte and Chris Kumaro. So in addition to the maneuver, we've done a long track scanning, which is really an innovative technique, I think, with these microwave sounders. I don't know if it's been done from satellites before, not to my knowledge. So the idea is that the cross-track scanning gives you a wide swath, which we need for coverage on the Earth. But if you turn 90 degrees and look a long track, then you can get many measurements of roughly the same atmosphere, close enough to the same atmosphere, from a lot of different incidence angles. And why would you want to do that? Well, one of the things is if you have a train of satellites in low Earth orbit, then you're viewing a single storm. The single storm is going to advect with the rotation of the Earth, and it's going to have the largest effect at the equator, and minimal effect up near the top of your orbit. And so the point is that then you're going to need to do the retrievals that we just showed for a variety of incidence angles, and know that so you may have multiple satellites that are well calibrated, but you want to find out if the retrieval does well at those multiple incidence angles. So here's an example of Tempest T retrieving total precipitable water and liquid water path. So water vapor and cloud water, retrieving it as a function of Earth incidence angle over a range of plus to minus 30 degrees Earth incidence angle. We do scan wider than that, but there are limitations into how far out toward the limb you can go in the retrieval. So they chose minus 30 to plus 30, and they show consistency across the at a given point when they're at a given point on the Earth, which would be equivalent to a given longitude. They show consistency in the color, and that basically the uncertainty or noise in making these measurements at different slant paths is small compared to the spatial variability, particularly in clouds, as you might expect. So then I would like to show a case where we observed storms over land in the southeast U.S. And here are the 5 channels of Tempest showing the storms. And then here's a retrieval, MRMS retrieval from ground-based radar. And this was actually a winter storm, and so the agreement was pretty impressive between Tempest T and MRMS. We've not published this, but we're looking at a number of cases over land as well. So the data are publicly available at tempest.colostate.edu, and we'd be happy if you could just register and then get access to the data, take a look at them, and see what you think. And I'd like to thank the NASA Earth Venture Technology Program for their support, and the NASA Earth Science Technology Office, ESTO, for their program management. Thank you very much.
Questions?
Yeah, hi. Actually, we did some evaluation with Tempest T data, and the data quality is quite impressive. And I just want to have two questions. The first is like earlier version, like 1.3 version, and before we noticed there are large like discrepancy in the geolocation. But in version 1.4, then the coastline alignment is much improved. Can you comment that or?
Well, okay. So those were versions that were made available to only a few people.
You're right, right.
And so so there was a why don't we talk offline about the correction? I mean, it's a correction that was made between 1.3 and 1.4 that needed to be made. And so if you want to get it in more detail, we can.
Yeah, okay. Then the other comments is really like you talk about the 164 gigahertz channel, and you say like the uncertainty is kind of larger compared to other channel, and that's because you were comparing with the meta of MHS, and actually we were told like the quite different between Tempest T and the MHS for this channel. We did our independent evaluation in this channel and the ATMS. Actually, the bias much smaller than what you hear. So you are showing here. So I think it seems to me it's like that bias, overall bias you are showing probably can be even lower.
Okay, thanks. I appreciate it.
Thank you.
I appreciate your interest in use of the data.
Just a couple things. Just a real brief note when you talked about long track scanning. Trim actually had done a long track scanning for a very short period. I think it was just a few orbits. And I think that JAXA did look at the radar data in that cross track scanning. I don't think we took advantage of the radiometer in a similar way. So just wanted to point that out. Just
I stand corrected. Thank you.
So thinking ahead here in terms of what's next, I'm assuming that you either already have plans moving forward with the fuller mission or putting in a proposal to do so. Would that be looking at also launching from the space station, or would you guys consider trying to put these into a train with GPM and complementing the science where GPM can provide the radar profiling and the GMI data coupled with the time derivatives that you can obtain from something like Tempest?
I've not thought a lot about that, about coupling it with the GPM core satellite in terms of orbit. I
bring it up because for ACCP, that's the type of thing we're looking at a lot.
Oh yeah, that's good. We should not be limited to the space station, particularly when we go up towards solar maximum. We need to deploy higher because just because of the attitude control capability. So it's not. It would work better if it's, let's say, well, even 450. 450 and above would work better for solar maximum. We've just been lucky in solar minimum, and actually our drag has been very low over. So the deployment was 15 months ago. We've made maybe 15 kilometers in orbit, so it should last some time.
Yeah, I was wondering if you could speak a little bit more about the data, just how much of it you're actually recovering from the satellite. You showed early on that you weren't necessarily getting all of it, but it sounded like that's improved. And also just, in the future, if you wanted to build more of these, how much, I guess, of the limitation to getting that data in both closer to real time and recovering as much of it as you can would increase the power requirement or something else in the hardware versus just being the cost issue of paying for time on those shared UHF channels or S-band networks?
Okay, it's a lot. It's not really a cost limitation in terms of UHF. It's really that there's exactly one station that is capable of downlinking our data right now. Now, I mean, we've been working on other stations. We may get another station in, but it's not, this is outside of the amateur band. This is FCC licensed because it's not operated by the government. So there are a few things that complicate getting more ground stations. But with one ground station, I would say we're getting, on the long-term average, maybe 40% of the data. But so if we got another ground station which had, and this ground station is operated up to, 16 hours a day for 5 days a week. And once in a while they'll do a weekend, but they have to be paid extra. So I guess that is a cost limitation. But they could be upgraded in the future to run weekends. That would help. But in the long term, I didn't cover it in the slides, but the Air Force plans to put the spare, because we have a spare instrument, onto the space station, along with COVER, an instrument, low frequency instrument that JPL built that you may be familiar with. Shannon Brown is the PI of that. So he's done the logistics with the Air Force. The general just signed off last month. So this should go up in 2021, and then we'll get full data, and we'll be able to fully exercise the instrument. So, the second copy of the instrument. So going forward, with future proposals, I would propose for S-band communications and to use a highly redundant, longitudinally extensive network of ground stations, like, CubeSat is one of them. And so that's really the mode that BCT has gone to since this. So this is already, a little bit older vintage of a spacecraft. It moves so fast, even though it's about, we finished it a year and a half ago. So yeah, we delivered it to the launch provider in March of 2018. So yeah, these things develop quickly. So then we could easily get 100% of the data, unless there's a spacecraft reset. But actually, that hasn't happened very much. I mean, we've been pretty fortunate. They're really about, in course of normal operations, there've been, over this 15 months, there've been maybe 6 spacecraft resets. So, did that cover your questions?
That was great. Thanks.
Okay, thanks.
It's a very impressive instrument. For example, the any delta T is pretty low. And is any further improvement in the future, like in the future generation of instrument? And because this CubeSat is very small, so any limitation because of weight and volume make you cannot make further improve. Like for example, for black body, will not target that weight and volume can find. So
no, I think the calibration we're happy with. The NEDT we're happy with now. Now, if you look into the future, then one of the things that one that I pointed to for twice that I didn't have time to talk about today. Oops. There. Yeah. This one has the next technology, next generation of low noise amplifiers from Northrop Grumman. So instead of a 35 nanometer gate length, it's 25 nanometer gate length. And so that allows us to go up to, we have in package right now in one of these modules, including integrated with the feed horn, we have 800 hertz. So we have basically 240, 300 some, and 670, 850. So we have those four for cloud ice profiling, cloud ice particle sizing, as well as sounding for temperature sounding at 118, water vapor sounding at 183 and 380, which has higher weighting functions. So other people have used 325 as well, gigahertz. So all of that is in this small package that, as I said, we're having our final review, and then we continue to do some. It would be a very adaptable for airborne measurements and so on. So this is the example of the next generation pushing higher in frequency. Now, in terms of the limitation, you can also think of the aperture size. So aperture size is a limitation in the 6U CubeSat structure. So you can imagine going to 12U, you could double the aperture, and then that would help you with spatial resolution. So we're looking at some other techniques to improve spatial resolution as well. But NEDT is not, I don't think it's the problem right now.
In a little technical question here. One is when you're using double differencing, what's your model? Use the transfer? Is it radius transfer model, or is it use some?
Yeah, radius transfer model.
So can I know what is radius transfer model used? Is it CRTM or is it what other model? I'm
pretty sure it's CRTM.
Okay, so if it's CRTM, I just wonder this CRTM coefficient is you come from where? From CRTM coefficient.
Yeah, I think we'll have to get into, I mean, okay. we'll have a review very soon that has all these details, and we can discuss a little bit afterwards.
Okay, thank you.
But the reanalysis data set.
Thanks. Even from what you just said a little bit about the aperture size and stuff, can you speculate like where this type of mission is going relative to the regular operational or even research low orbit missions? Are you always going to have these being different from them? Are they going to converge in some way? Are you going to have one big one and a lot of little ones? What do you think is going to happen?
Way above my pay grade.
So, go ahead.
Yeah, I mean, I think that's for, NOAA has a BAA out right now looking for opportunities for the future for LEO and for GEO. So we'd be interested in LEO, right? And so it's a good, I don't have a crystal ball in terms of what's going to happen, but I think that we should, we should populate, we should try to populate some orbits with a constellation of a Tempest-like radiometers and see what we get. See to what extent they contribute, and then scale up from there. So I don't, and then I don't see it replacing operational sensors right now, but I see it as a question that goes on for the next 5-10 years, and then for research, well, there's some interesting. I think it provides some interesting opportunities, and I gave the example of temporal resolution. Yeah, so or more frequent updates to tropical cyclone forecasts. That's very interesting too. So I think we should think about, as a community, how do we integrate these small satellites in? What is their lifetime? BCT just told me they have one on orbit for operating for over 3 years, even though the science mission ended, or the technology demonstration, I guess it was Invest Raven, it's called. It's a 3U CubeSat, and with carbon nanotube sensors looking at long-wave radiation from the Earth. And so they were at a much higher orbit, you know, because they were looking at the whole Earth disk and radiation, you know, total radiation. So, so I think that, you know, I think there's some interesting opportunities to infuse new technology, and then if you can build up a reliability long enough, you know, a long enough time series to contribute to climate measurements, maybe by using a number of them, maybe by having, you know, a dozen up there, let's say, and then replenishing when they start failing, having ones to launch every so many months, right? And then maybe having a calibration transfer standard on a larger satellite, some kind of calibration standard that can actually become NIST traceable. Chris Kumro talked about this at the AMS Satellite Conference.
Okay, so with that, let's conclude and thank the speaker again.
Thank you. Oh, do we have any questions from the web? Okay. Okay. Hi.
I want to introduce Scott Brown.
Oh, yeah. Sure. Sure.